Today we are going to start new topic called Operational Amplifier Opam. Now the Opam that we use in our lab consists of 8 pin The left hand side start with counting 1, 2, 3, 4, 5, 6, 7, 8. The pin 8 is not connected. 1 is offset null and 5 is offset null. Second is inverting terminal. Third is non-inverting terminal. Fourth, we bias with negative supply. 7, positive supply, and 6 is the output. This is mu A 741 or OP07. This we are going to use in lab as well as in simulation purpose. The internal architecture of Opam is this. This is negative terminal, this is positive, this is your pin number 2, this is your pin number 3, this is pin number 6, and this is pin number 4, this is pin number 7. Here negative biasing, here positive biasing. As we bias the transistor, same way we have to bias the Opam. Now in Opam we have to give dual supply. Dual supply, one positive supply and another negative supply. Now if we don't have the dual supply in our lab, then how we create the dual supply? Just take two voltage source. The negative terminal of one voltage source connected with the positive terminal of another voltage source, and it is grounded. The positive side will be giving your positive biasing, negative side will be giving your negative bias. This is supplied to pin number 7 and this is supplied to pin number 4. Like this we can get the positive supply as well as negative supply. Now internally Opam consists of 20 transistor, 11 resistor, 1 capacitor. This one capacitor plays very important role in frequency analysis. There are many applications of Opam that we will learning in due course of time. Now, going through the Opam structure, the mathematical model or the circuitry model of Opam. Means with the help of our linear element like resistance, voltage source, we can represent Opam. Now this is your Opam. Inside Opam, this is very high resistance, which is denoted by Rn. This is very high resistance, and the output is given by, this is V epsilon, voltage between these two terminals. Then output is given by A into V epsilon, and this is your R naught. Now the purpose of Opam is to amplify the voltage which is appearing at the input terminal. V epsilon is the voltage across input terminal, and what does Opam did? It amplified by quantity A. Now ideally we will be taking three terms only right now: ideal behavior of R in, R out, and A. Ideal behavior, it is infinity, this is 0, this is infinity. Practically it is in mega ohm, it is approximately 75 ohm, and this is 10 to the power 5. Now one can say when A is tending to infinity, means by any amount we can get the gain. If we are giving, suppose if we are giving 1 volt and A is 10 to the power 5, then V naught will be A into V in, which is nothing but 10 to the power 5. But we are not going to get 10 to the power 5 voltage, because this output voltage is being limited to the biasing voltage. The biasing voltage is up to plus minus 15 volt or plus minus 12 volt. So output voltage can maximum vary till plus minus 15 volt. Now we came to know that output maximum it can vary to plus minus 15 volt, and we know A is 10 to the power 5. Now we have equation V naught is equal to A into V in. V in equal to V naught by A. V in equal to V naught is plus minus 15 volt. This is 10 to the power 5. Now it comes to 150 microvolt. Now V in, what is V in? It is nothing but the difference in voltage between terminal V1 and V2, or V2 minus V1 is equal to V in. This is the voltage that is being applied across terminal 2 and terminal 3. So if the difference between V2 and V1 is 150 microvolt also, then it will lead to output voltage of 15 volt, because V0 is equal to 150 microvolt into 10 to the power 5, it is nothing but 15 volt. So Opam can detect even a small difference in voltage of 150 microvolt. So this is one of the most important point of Opam. Now when we say V2 minus V1 is equal to V in, and V in we have calculated 150 microvolt. Now we can say V2 equal to V1 plus 150 microvolt. It means V2 equal to V1, because we can neglect this voltage to 0. So this is called virtual ground concept. Means whatever the voltage is at terminal 3, the same voltage will appear at terminal 2. Means virtually it is grounded. If suppose this is having 10 volt, then terminal 2 will be also having 10 volt. This is your virtual. Suppose this terminal is having 0 volt, terminal 2 will be also having 0 volt, because there is only a difference of 150 microvolt. So we can say Opam work as short circuit. Now we have seen the Rin. This is your terminal 2, terminal 3. Now we said about the Rin that it is ideally it is infinity. Means it will not allow any current, any amount of current to enter across this terminal, because this Rin is very high. When this will not allow any I to flow across the Opam, it means Opam act as short circuit. It means simultaneously Opam is working at short circuit as well as open circuit. Here it is acting as a open circuit, because it will not allow any current to pass through this one. So we will assume that this is open, that's why it is acting as an open circuit. Now it is simultaneously acting as a short circuit as well as the open circuit. Short circuit because the difference between V2 and V3 is only 150 microvolt, and open circuit because Rin is very high. Now lastly we are discussing about the R0. Now we said about the R0, this is very low. It is almost equal to 75 ohm. So while simulating we will look upon this feature. So this is all about your basic characteristics of Opam. Now going to feedback. this is your Opam. This is your 6, this is 4, 7, 2, 3. Now we are making this with the black box having again A and having input B in and output BO, where BO is equal to A into B in. This we are representing because Opam gives us gain of A. Now feedback can be positive feedback as well as negative feedback. We are going to study negative feedback. Negative feedback means there are 3 boxes. We will first study about these 2 boxes. This is your mixer circuit, this is your sampler, and this is nothing but your A, this is your Opam. Now what does sampler circuit do and the mixer circuit do? That we will study, then we will look upon the negative feedback system. Now we know one thing, that whenever there is voltage, if we want to measure the voltage, we just tap it parallelly and we connect voltmeter across this. Now if we need to tap current or measure the current, then we put a series ammeter across this one. So if we want to sample, there are 2 quantities only, voltage and current. So voltage is tapped in parallel and current in series. Why voltage is tapped in parallel, we got to know. Now mixture circuit. Suppose we want, this is the input side, and we want to feed the current, so it will be fed parallelly, or then only the current over here will be I out will be I in plus I1, which is coming I in plus I1, or I0 will be I in minus I0. If we want to mix voltage across this one, then we have to add in series. This is the voltage we are adding. This is the addition of voltage in series. This is something we do if we are adding. Then this is being added. So we got 2 points. First, sampling of voltage is done in parallel manner, parallelly. Current sampling is done in series way, and for mixing we do mix the voltage in series and current in parallel. As there are 4 feedback, the first one is voltage series, second voltage shunt, third current series, fourth current shunt. Now we will study one by one what all the sampling process. Now taking voltage series. Voltage series. What does it mean? Means this is your Opam A. This is your output voltage. We will tap the voltage in parallel manner and we will feed it through some beta factor. This consists of resistance. Now this is your V0. Some amount of V0 is tapped and it is fed to in series. This is nothing but beta V0. This is beta V0. This is V in. Here what we are having, V epsilon. Now V0 is equal to A into V epsilon, because the work of Opam is to amplify the voltage across the input terminal. The input terminal what we have, V epsilon, and this is getting amplified by times A. Now this is the sample we have done, voltage sampling, and the what voltage we got, beta V0. This beta V0 is now being fed. Now we got V0 as A into V epsilon. Now V epsilon is nothing but V in minus beta V0. Now V0 is equal to A into V in minus A beta V0. Beta V0 is equal to 1 plus A beta A V in. Now V0 by V in, A by A plus A beta. Now again this is a gain, this is called closed loop gain, A by 1 plus A beta. Now what we have observed, the first observation, that the gain got reduced by 1 by 1 plus A beta times. Now we know that A is infinity. Now applying limit A tending to infinity to a function A by 1 plus A beta, we have A taking A common, 1 by A plus beta, this A got cancelled. Now putting A is equal to infinity, 1 by infinity plus beta, this is nothing but 1 by 0 plus beta. Now we got 1 by beta A closed loop. So this beta is in our control. So this way the voltage series can be very useful and we can set up the gain in our favor. It can be, we can set beta to be 10, 20, 50, 100, any amount we can set by just making R2 or any resistance in our favor. Now we are just going to look voltage series again with the help of the circuitry model. What is this circuitry model? We have studied this one. This is A B epsilon. This is R0. This is Rn. The voltage across this is V epsilon. And this is your positive terminal, this is your negative terminal. Now this is your voltage series. Now this voltage is V. This is the voltage and this is your R0. Now I am not writing R0 here, I am just making it parallel. And this is your ground. Now this is being tapped. This is the output voltage. Output voltage is nothing but A into B epsilon. Now this is being tapped. Now we will tap it by some resistive network. This is your R1 and this is your R2. This is from here we are supplying it to negative terminal. Means this much amount of voltage we are feeding to, we are tapping this much amount of voltage and we are feeding in series. So this is our V in, we are supplying it. The current will be I in. Now we can say B epsilon is nothing but I in R in. This is we can say, or we can also say what is this voltage that we are applying. It is nothing but A B epsilon in R2. What is the voltage across this one? This is nothing but total voltage across this one into R2 by R1 plus R2. A B epsilon into R2 by R1 plus R2. Now treat this value as a beta. Now this it became A into beta into B epsilon. Now applying KVL across this loop, what we can write? B in minus B epsilon minus A beta B epsilon equal to 0. Now B in is equal to B epsilon 1 plus A beta. Now B epsilon is nothing but I in R in 1 plus A beta. Now B in by R in is R in plus 1 plus A beta. B in by R in is nothing but closed loop input impedance. Now what we are saying, that it is being increased by factor 1 plus A beta. Initially what we have seen, that with voltage series feedback our gain is being decimated by 1 plus A beta, and here our input impedance is getting increased by 1 plus A beta. It means 1 plus A beta is taking a great deal or great part in decimating or incrementing the value of R in or A. Now this is A. Now we have V naught is equal to A into B epsilon. Now can we do anything about this one? V naught is equal to A into B epsilon. Now we can say R naught is nothing but output and impedance. This is your output voltage, and output voltage will be nothing but I0 into R0. And when we will rearrange the circuit, then we will see R0 is being reduced to R0 by 1 plus A beta, the R0 closed loop output impedance. Closed loop output impedance is getting reduced to R0 by 1 plus A beta. Now we are not going to make all this calculation in each type of feedback. So we will make a small assumption and we will try to figure out how to check whether it is increasing or decreasing. We just need to know if it is increasing, it will increase by 1 plus A beta. If it is decreasing, it must decrease by 1 plus A beta. So we need to get one idea how to decrease or increase, how it is being done. So we will formulate one block diagram. See, now in terms of resistance only, if we need to take Thevenin's model only, so what we will do, suppose this is the model of Opam. Now taking Thevenin's, what we will do, we will sort the voltage part. Now how we can write? This is your Rin and this one R0. Now this will become your A. Now we need another block in the same manner. This will be your beta. This will be the beta. Now we can call this as a beta, R beta not, R beta in. This is the name we are given. Now this is the structure that we will be using always. Now this is we will be using for voltage series. Now what we do in voltage series, we just tap the voltage parallelly and we put in series. Now if we look across this one, we see that resistance is R in and R beta in is in series. So R input is being increased, and we have seen by the formula that R in is increased and it is increased by 1 plus A beta times. So R in will become R in into 1 plus A beta. Now R0, if we look across this one, this R0 and beta R0 are in parallel. So output resistance is decreased and will decrease by 1 plus A beta times. Now this is your voltage series. Now in voltage series, we tap it and feed it in series. Now when we are feeding it in series, then here voltage is increasing. So it is voltage controlled voltage source. So we can say voltage controlled voltage source. In the same manner, we are going to look all the circuitry. Now we can design one circuit using this voltage series method. What is that circuit? This is terminal 2, this is terminal 3. We are taking V in and this is ground, means we are tapping some amount of voltage. This is R2, this is R1. We are tapping, this is V0, this is your RL. So we are tapping some amount of voltage and we are directly feeding to negative terminal. So this tapping is done in parallelly, and what we are tapping voltage and we are feeding it in series. So this is called voltage series. Now according to virtual ground, if we need to solve this circuitry in terms of V0, Vi and A, what will be with that? How we will solve this circuit? Now because of virtual ground, this is V in, and because of virtual ground, this voltage will be also V in. And if suppose current I is flowing over here, now this I will flow across this resistance, but it will not move inside the Opam because here it is very high resistive path. So this I will move across this one circuit and this will just come out. So we need to just apply KCL at this point. Now applying KCL at point at point B. So V in minus 0 by R1 must be equal to V0 minus V in by R2. Now V in by R1 is equal to V0 minus V in by R2. Now taking these as one side, V in 1 by R1 plus is equal to V0. Now V0 by V in is 1 by R1 by 1 by V0 by R2. V0 by Vn is nothing but this is your equation. Vn 1 by R1, this came left hand side. Now this became Vn 1 by R1 plus 1 by R2. This is that V0 by R2. Now if we need to calculate V0 by Vn, then it will be R2 into 1 by R1 plus 1 by R2. Now we got V0 by Vn nothing but R2 into 1 by R1 plus 1 by R2. This is nothing but R1 into R2. This will be R2 plus R1 and this is R2. This will get cancelled. Now this will be 1 plus R2 by R1. Now V0 by V1 is nothing but 1 plus R2 by R1. Now V0 is nothing but beta into V1. Here beta is 1 plus R2 by R1. So we can control our beta by changing R2 and R1. If we keep R2 as 100K and R1 as 50K, then beta will be 1 plus 100K by 50K. It is going to be 2. Now beta will be 3. Now this is your beta or the gain we got in voltage series. Now we are left with three more feedback that we will look in next classes.